Oh, hi everyone, and thanks for coming to the last session of this semester of DOTS. And also, we just noticed that it's basically the 6th birthday of DOTS. So it was like April 21st, 2020, the first session. So yeah, we basically entered primary school. And so the first talk of today is gonna be by Marius Roland, and he's a permanent research associate at the Inria in Lille, in France. And he started there in January 2025. Before that, he was a postdoc in Montreal at Polytechnique. And even before that, he got the PhD in mathematics in Germany, in Trier, with the Professor Martin Schmidt. And his main research interests are optimization under uncertainty, MIP in general, combinatorial optimization, and machine learning. And today he's going to talk a little bit about disjunctive programming.
Okay. Thank you, Sylvia, for the very kind introduction. Before starting, I wanted also to thank the organizers for this series of talks. I think it's a great opportunity, especially being a young researcher, to show a little bit some of my work here. So the title of my talk today is Multidimensional Disjunctive Inequalities for Linear Chance-Constrained Problems with Finite Support. So in a nutshell, my aim today is to present to you a new family of valid inequalities that can be used to tighten the linear relaxation of linear chance-constrained problems with finite support. So before I start presenting this family, let's take a step back and start from the ground up. So introduce again chance-constrained problems. So for some people, this will be a bit redundant, but I think it's important to set the stage a little bit. So chance constraints are concerned with the following question, which reads, how much attention do extreme events deserve? So this, in fact, relates to stochastic programming in general. So when we do stochastic programming, we try to take into account uncertain parameters that drive the decision-making. And these uncertain parameters can take extreme values. So these are often referred to as outliers, for instance. And so in some cases, for instance, if you think about robust optimization, these extreme events will very heavily influence the decisions you obtain. So this might be a bit restrictive in practice. And so this led to the invention of chance constraints. So 70 years ago, approximately, people developed the idea of taking into account the uncertainty while being able to abstract from some of the extreme events that will otherwise very heavily influence the decision making. And so this is the idea, the fundamental idea of chance constraints. So let's formalize this a little bit mathematically. And so here I've shown you a very generic version of, let's say, a stochastic program. So we have a generic objective function, a set of decision variables. So this is not important. What I'm interested in is the fact that X needs to be inside of a set capital X, which is dependent on an uncertain parameter Xi. And so as I told you, we want to take this uncertainty into account. So the robust way, for instance, would be to say that we want this inclusion to be satisfied for any possible value of Xi. So there's different ways of writing this robust version, but one that connects a lot to chance constraint is the following. So we would say that the inclusion is satisfied with a probability equal to 1. So this, in fact, corresponds to the fact that we're 100% sure that the inclusion is satisfied. And as I told you, this can be quite restrictive. So we will relax this a little bit. And this brings us to the idea of chance constraint, where we instead want the probability to be satisfied with we want the inclusion to be satisfied with a probability almost equal to 1. So in this case, we would have 1 minus a small threshold value, which could be, for instance, 0.05. And so we know that in this case, for 95% of the cases, the inclusion is satisfied. Okay, so this is conceptually what chance constraints are. So now I've kind of given you some introduction to the topic. I will further specify the setting. So this refers to the words linear and finite support that were in the title. And then once I introduce these specifications, I will show you what the associated challenges that come with these specifications. And this will allow me to motivate the idea of relaxation strengthening, and more specifically, look at the idea of developing cutting planes for such problems. Then I will introduce the new family, discuss some numerical experiments, and finally, I will conclude. All right, so let's specify the setting. So first part of the title is the finite support assumption. So this refers to the fact that the uncertain parameter is part of a finite set. So this is very classical in practice. And so each of these observations corresponds to what we call a scenario. And so the set capital S captures all of this information. So further with these scenarios, we now have a fixed probability, so a deterministic probability. And each scenario also has a fixed feasible region. So this corresponds to evaluating the set at the observation. And using this information, we can reformulate our model in the following way. So this is really the discrete version of the chance-constrained program. So it's the finite support version. So now we introduce one binary variable for each scenario. And this captures, let's say, the satisfaction of that scenario. So if X is inside of the feasible region of the scenario small s, then the indicator function becomes equal to 1 and the binary variable equals 1. If the binary variable equals 1, we add the probability here to the left-hand side. And so this is really, let's say, the discrete alternative of what I presented earlier. Okay, so this brings us to the first challenge. And for this, I constructed a very tiny example that should give you some intuition on why these problems are hard to solve in practice. So here I assume that I have three scenarios. So there's a red scenario, a green scenario, and a blue scenario. And each of these scenarios now corresponds to one of these feasible regions. So X is two-dimensional. And so if you satisfy one of these scenarios, you need to lie inside of this feasible region. In addition, let's assume that the probability you see here is 1 over the size of the scenario set. So each scenario is equiprobable. It has the same probability of appearing. And let's say we also assume that the threshold value, so the amount of uncertainty we're able to ignore, is also equal to 1 over 3. So in this case, it just corresponds to saying that you need to satisfy 2 out of your 3 scenarios, and you can also ignore 1 out of the 3 scenarios. You can rewrite this in a very straightforward way, which in this case tells you that you need to satisfy always 2 out of your 3 scenarios. And so if we want to look now at the first challenge, let's construct the feasible region of these X variables. And so to do so, we each time needs to take 2 scenarios and lie inside their feasible region, so lie at the intersection. We can do this. So let's take the red guy and the green guy. We get this. If we take blue and green, we get this. And if we take blue and red, we get this. And so here the challenge immediately comes in a very natural way. So you observe that your feasible region is in fact non-convex and non-smooth. And in addition, you can even make it disconnected. So these problems are very hard because of this reason. A second point is that there is a very combinatorial aspect part of these models. And you have this kind of binomial aspect of each time having a bag of scenarios and needing to satisfy some of the scenarios, or you could also see it in the opposite way. You can ignore some of the scenarios. All right. Very related to this question. So it has been shown that it's NP hard to solve even for simplified cases. Okay. And now the second part of the title refers to the linear assumption. So this means that everything is linear in the model. The feasible regions are described by a set of linear inequalities. The objective is linear. And in addition, I will assume that, as I did earlier, the scenarios are equiprobable. So this is not necessary for everything I will present today, so the equiprobable assumption, but it's useful to simplify everything. And so now we go from the model I showed you earlier to this model you see here. So I replaced the inclusion by the set of inequalities, and I took the 1 over S and put it to the right hand side. So one thing that is nice in this, let's say, discrete version is that the left-hand side here is fully integer. So you can round up the right-hand side. And this, in fact, since the set of your set capital S is also an integer, it in fact just comes down to rounding down this part. And so what is very important to realize in this model is that now your chance constraint looks like this. And this is your total amount of scenarios. And this number here is the amount of scenarios you're able to ignore when constructing your feasible solutions. Okay, and finally, your objective is. Okay, so now I've specified the second, let's say, assumption. And so this brings a very classical challenge in mixed integer linear programming is reformulating indicator functions. So if you make some rather straightforward assumption, for instance, about your feasible region calligraphical X here, you can usually reformulate this with big M constraints. So this is not the only way of doing, but this is what people usually do. And in fact, it's well known that big M constraints can lead to very weak continuous relaxations. There are some papers on this. But if you look at the model fundamentally, if you abstract from these constraints here and the change constraint, most of the constraints inside of the model are just big M constraints. And so if we even, for instance, want to look at numbers, let's say you have 1,000 scenarios and 10 constraints per scenario. This means you have 10,000 big M constraints. So these problems tend to have a very weak linear relaxations. And this motivates, in fact, the topic of the presentation, which is more specifically cutting planes, but in general, the idea of strengthening the continuous relaxation. So today I'll be talking, as I told you, about these multi-disjunctive inequalities. So I don't have time to go over the entire literature, but what is quite important, or some previous works, let's say, are the works on quantile inequalities and mixing set inequalities. And even more important, the following paper that talked about what they call simple disjunctive motivated our ideas in our paper. So you could see the ideas I will present later as a generalization of what they do in 2 dimensions. So the first thing is that in this paper, they focus on a specific type of chance-constrained program, and they take advantage of a disjunctive aspect, which we then further extend in our work. Okay, so now that I've set the setting and I specified all the details, let's look at the main contribution of our work, which is the multidimensional disjunctive inequality. So for you to get some intuition on the disjunctive idea we take advantage of, let's look at a rather straightforward example. So let's say we have 5 scenarios, which you see here. So these are let's say, the scenarios in our bag. And we're able to ignore 2 scenarios. So each time we will have to satisfy 3 out of the 2 scenarios, and we can take any possible combination. So we could ignore these guys, we could ignore these guys, anything works, right? So now to construct a disjunctive argument, let's say we select a subset S bar, which has 4 elements. We can very easily find some argument that tells us that some scenarios need to be inside of this set needs to be satisfied. So if we now try to ignore some scenarios, for instance, this and this guy, or this and this guy, we observe that there is always some scenarios inside of this bag that are satisfied. And so we can very easily show the following arguments, which tells us that there is at least this amount of scenarios inside of the bag that are satisfied. And in fact, if we make a good selection of scenarios, so let's say we take very bad scenarios or scenarios that are very hard to satisfy, then we can, in fact, usually find some scenarios that necessarily need to be satisfied when we make this complete bag. Okay, so that was the idea. Let's now use this to construct a valid inequality. So before doing this, I will simplify the setting a little bit. So I will go from a set of inequalities for each scenario to only one inequality for each scenario. And this will simplify the notation quite a lot. So let's again assume we select a subset S bar that has the following size. So it's at least greater or equal than tau S plus 1. So there necessarily is at least one guy that needs to be satisfied. And in fact, we know that there is at least this amount of scenarios that need to be satisfied inside of the set. But the scenarios that are satisfied inside the set necessarily depend on the solution you're considering, because you can each time ignore different scenarios, right? And so we can introduce the set here that we will call S hat. That will be, in fact, solution dependent and will correspond to the scenarios inside of the set S bar that are not ignored and that are necessarily satisfied. So using this set, we can construct what we call, what I will call a local inequality. So this is only valid for the solutions that satisfy the specific scenarios inside of S hat. And it looks like this. So what we do is we take all of the scenario constraints of these scenarios that are satisfied, we sum up the left-hand side, we sum up the right-hand side, and we identify the coefficients in front of the variables here, and we just sum up all of the right-hand side coefficients. And so this inequality is valid only for the solutions that satisfy these specific scenarios. And so what I'm going to do afterwards is show you that whatever selection you make, you can always find coefficients for these parameters, or let's say, sorry, you can always find an upper bound on these coefficients that will produce a valid inequality for whatever selection of scenarios you need to satisfy inside of S hat. But let's do this now. And in fact, it's rather straightforward. So this is quite a classical technique, I guess, in disjunctive programming. So this is your coefficient. What I'm just going to do is find a greedy worst case combination of the coefficients inside of S bar that is necessarily an upper bound on this guy. And in fact, you can rewrite this greedy selection as a linear program, which looks like this. And so if you look at the linear program, you should get a very clear view of what I'm doing. So here I have variables WS that will select or not my scenarios to be part of my coefficient. And so I'm just doing a greedy maximum. So I'm just selecting exactly this amount of scenarios until I get, let's say, the worst case upper bound on my coefficient. And since I know that there is at least this amount of elements that need to be satisfied, I know that this will necessarily be valid. And so I can do the same, in fact, for my right-hand side, which you see here. And again, I take the greedy worst case, but now instead of taking the maximum, I take the minimum. And this then produces a valid inequality. All right. Here is now a quick short summary of what I presented. So we take a subset S bar, we make sure it's big enough, and then we compute our coefficient by always taking a greedy worst case of exactly the amount of elements we need to satisfy. All right, so I made this assumption of having one inequality per scenario. However, in practice, as I told you, we can have more inequalities per scenario. So what we do is rather straightforward. We introduce a multiplier lambda s for each scenario, which will, in fact, concatenate our constraints into one inequality. And so this parameter lambda s is now part of the parameters of my inequality family. Okay, so this is something I can change as well. And so when I do this, I know that I necessarily obtain one valid inequality per scenario, which I can then use to do exactly the same machinery I was doing before and get something that is again valid. So here is again a little summary of what we have. So we compute these multipliers that produces one good valid inequality for each scenario. And then using the subset S bar, we compute these valid upper and lower bounds, which gives us something that is valid for our entire problem. Okay. I won't get too much into detail. I don't know how much time I still have left, but in the paper, we have interesting closure properties. And I think without getting into too much detail, but what I can tell you is that for the worst case, our inequalities, or let's say their closure, is equal to the quantile inequality closure, which is also equal to the projection of the mixing set closure. In some cases, we're able to construct very tiny instances where the closure of our inequalities is a proper subset of the other families of inequalities. And so this shows that at worst, you're as good, but in general, you might be better. For separation, I won't get too much into detail again, but we show that the separation of the inequalities is NP-hard when the size of the scenario set is fixed. So this doesn't mean the family is necessarily NP-hard to separate. And in addition, we can show the following nice properties, which I won't go too much into detail, but based on this, we construct a separation heuristics, which, as I hope you will see, is quite good from a numerical perspective. Okay, so let's talk now a little bit about numerical experiments. So our idea was to test these inequalities against other families of inequalities, more specifically the quantile and the mixing set inequalities. To do so, we consider multidimensional knapsack instances from the literature. So what people usually do is that they take a base multidimensional knapsack instance, which they then perturb. So they take each entry individually, perturb it using a normal distribution, and this then produces individual scenarios. And so if you want to kind of visualize what happens in practice, you can look here at the left schematic. So in black, we have the base instance. So this is a visualization, okay? It's not exactly what happens with the multidimensional knapsack, but it should give you some intuition. And then using this base instance, they perturb each element, and this gives them these individual dashed lines, which each corresponds to the feasible region of one scenario. And so we realized that since our inequality family computes a lambda multiplier for each scenario, it would probably be even more robust if we generate the data in a different way. So instead of doing this, we propose to also take, let's say, two multidimensional knapsack instances, which are each going to correspond to 50% of the scenarios. And since our method computes these lambda multipliers, we will get good inequalities for each scenario, which can then be combined into a good multidimensional disjunctive inequality. Another thing is that for the quantile inequalities and the mixing set, these inequalities don't do this in practice. And so, as you will see, they are not very robust when this method, let's say the method of instance generation changes in practice. All right, so the first experiment we carry out is a pure cutting plane setup. So We add cuts until there's no cut to be added anymore. And we compare, as I told you, against quantile and mixing set. So these are the results of the experiments. So here you can see the instance information. So this is a multidimensional knapsack with 20 variables and 10 constraints. This is the literature method, this is the new method, and this is the amount of scenarios. This is the gap close. This is the time to separate one inequality. This is the number of cutting plane rounds that are applied. And that's it. So I think here the message is quite clear. So in general, we cut more. And I think what is very important and related to what I was saying earlier is that for the new method, we don't lose much performance, whereas these other methods have way more trouble to cut more, especially if you look at, for instance, the quantile. Okay, so this was cutting plane. So let's now have a look at the MIP setup. So we start by doing the cutting plane in the root node, and then we run the MIP solver afterwards. So these are the results. So here it's again the same type of table. We have the generic MIP and then all of the inequality families. So I think here the message again is quite clear. So in general, we cut more. Just one detail. So what you see here is the gap closed, and in parentheses the number of instances that are solved to optimality, because in fact we replicate the experiment 5 times. This is why you see this. And if all of the instances are finished before the time limit, then we just show the average time. And so I think here again the message is quite clear. However, for instance, these tiny instances with 100 scenarios here and here, you can see that we're less good. And I think this is because in the end we add, so the multi-disjunctive inequalities add a lot of inequalities. And so it takes more time, whereas we could probably immediately go to the solver, and this somehow impedes on the time the solver needs in the end. Okay, so that was it. Here is a general conclusion of my work, and I think it's everything I want you to keep in mind for today. So I will go over it because I think repetition is useful. So I introduced you to this problem of linear chance-constrained stochastic programs with finite support. I specified the setting and showed you this non-convexity issue and the fact that these problems have a very weak LP relaxation. I talked a little bit about quantile and mixing set inequalities, but if you're interested about this, we can chat a bit about this later. And finally, I introduced really the main topic of today, which is these multi-dimensional disjunctive inequalities. We showed that there is a theoretical dominance of these inequalities. So at best, they have a better closure, and at worst, they're equal to the quantile and the basic mixing set closure. And finally, I think from a computational point of view, you saw that we had better performance and we were more robust. So that was it. Thank you very much.
Thank you very much, Marius. So in the interest of time, we will put all the questions later on. Marius will be available for the breakout room. So